I'd like to welcome everybody to this special panel that we have today on innovation in oncology. When things don't work in oncology, and they still very often don't work the way we want them to work, people are asking again and again, what could we fix? What could we change? How could we accelerate it? I don't think there's ever been a period that has seen this much innovation in any scientific area as we are seeing today in oncology. It's driven by tremendous need, to be sure, but it's also driven by tremendous scientific opportunities that have been laid out by decades of work understanding the actual basis of cancer that are finally paying enormous dividends. So the Biden Cancer Initiative has organized backgrounders on important topics, and this is the backgrounder on innovation in oncology. And we are lucky enough to have today 5 amazing speakers, all of whom are very active in entirely different areas, to tell you a little bit about what they do and why it's exciting. So I'm delighted to introduce our next speaker, who is Professor Regina Barzilay. She is the Delta Electronics Professor in the Department of Electrical Engineering and Computer Science at MIT. And until 3 years ago, she was not working on cancer at all. She is a world expert in natural language processing and machine learning, who, through her own experiences, came to be interested in the problems of cancer. And as an expert in computer science, she looked at what was going on in cancer and asked, how come cancer isn't taking advantage of everything that computer science has to offer? And so over the last 3 years, Professor Barzilay has brought to oncology innovation in machine learning, and she will tell us all about it. Thank you very much.
Hi, I would like to talk today about how machine learning can change cancer treatment. So, as Eric said earlier, I'm a computer science professor, and until a few years ago, I never worked on anything related to medicine. However, in 2014, I was diagnosed with breast cancer, and here you can see my son cutting my hair after my first chemo. And the thing that was really horrifying was not even the fact that I got cancer. The thing that was horrifying to me, that today the algorithm that recommends you Snickers on Amazon is much more sophisticated than the algorithms that are used to recommend treatment. That we are living in the world that every hospital sits on lots and lots of data, and we cannot, as patients and also as physicians, to get basic information about the course of care. And looking at that, when I came back to MIT after my treatment, I decided I absolutely have to do it and to change it. The first idea that was clear to me where machine learning can change is actually how do we match patients to cure. So today, we collect a lot of data about the patients, the raw data, the mammograms, the pathology slides, it's all digitized. It's extremely high-resolution images. But what happened next? We have a human who reads those images and summarizes these hundreds of thousands of pixels in a page or two, losing all the personal information about the patient. And then it's not even what the physician is looking at. At the end, we have some categories, human-defined categories, that based on these categories, like for instance in case of breast cancer, it can be ERPR and other measurements, we decide about the cure. So this whole treatment pipeline, which is not specific to breast and which is common in many other cancers, is actually an example how we are losing personal information. And now if we are looking at 4 patients with breast cancer, which in terms of variables are exactly the same, we cannot explain why 3 of them were fine and 1 of them recurred. Because at the level of this abstraction, we already lost all the important information and we cannot recover it. And now I want to show you a statistic which I personally find horrifying. This is a statistic that comes from American Society of Clinical Oncology that tells that today all the cancer treatment are based on 3% of the population that participates in clinical trial. Now, you don't need to be computer scientists to believe that in any other area, people who work with data never throw out 97% of the data, and doing that, we really lose our ability to personalize. So again, when I came to MIT, what I believe we should do, we should take all the raw information that we have about the patients, and we collect this information, and directly from these raw measurements to provide probabilistic models that can predict answers to the questions that we care about, which would be sensitivity to treatment, high-risk population, disease progression, and many other things. So the first thing that we needed to do is actually to take data about the outcomes and translate it into a database form, because machines today cannot really go and read documents. So what we've done, we took the data, the pathology of the breast cancer patients that were treated across the partners institution in the last 3 decades, and we put it in the database automatically using machine learning. So now you can query and get the patient population with the specific features you're looking at and see what happened to them. And now this is, in terms of computer science, it's really kind of plumbing problem. It's very simple. Now let's see with this very simple piece of technology what you can achieve. Let's say you want today to study a precancerous condition like atypia in breast cancer. Today, in New England Journal of Medicine, you can get a paper about atypia with 674 cases. Now, you may be asking yourself, why so few? Because it's millions of women in this country have this condition, and the reason comes in the first paragraph that they say that they had to go by hand through 10,000 patients to identify 674, which had specific thing. Only at MGH, with one query, a second query can give you 6,000 patients with this condition. So what we can do is actually move this study from very small boutique experiments to really large-scale analysis that we need to understand how disease changes. Let me give you another example how this data can help you. Predicting overtreatment. Today, when the doctor is uncertain, typically they go for the most conservative treatment that you can take. So for instance, if you're a breast patient and you were diagnosed on needle biopsy with high-risk lesion, 100% of these patients in Massachusetts General Hospital get a surgery. Only 13% of them actually had cancer. So the rest of these women get a surgery which they didn't need. And now with machine learning, with the data that we automatically extracted, you can already reduce 30% of patients that didn't need the surgery in the first place. And obviously we can do more and find even more benign cases. But the idea is that today, unless the human gets some help from probabilistic model which can help them to deal with uncertainty, we will be unable to really cut unnecessary treatments. Now, what I personally believed, that okay, you can extract that much information from what human actually wrote in these notes, but the real answer to the questions are in raw data, in images. And I want to share with you my personal mammogram that was taken, from 2012 to 2014. And here you can see my tumor when I was diagnosed in 2014. Now look at it in 2013 and 2012. And here you can see it in the magnified form. So what we can see here, that I was misdiagnosed by 1 or maybe 2 years. And apparently this is not a very unusual finding. There was a recent paper that showed that 30% of high-risk patients, which were screened on MRI, were already had a tumor year before they were diagnosed. So the question is, what machine learning should be doing? Should machine learning actually trying to do what humans are doing? And I don't believe so. They should be doing things that humans cannot do today. And we developed a lot of tools that currently are already in the clinic at Massachusetts General Hospital. And here you can see my collaborator, Dr. Connie Lehman, and other radiologists at MGH, which are already using deep learning technology to analyze the images and help with many assessments. And you see her that she reads the image, she looks at it, gets the assessment, and afterwards she approves it. Now, the interesting question for me is actually how early you can say that the patient is going to have cancer. And I'm not talking about the cases where the human can see it and maybe miss it because they were distracted. But we know from biology that it takes a long time to actually develop cancer. And we already start looking at the deep learning models that can take the image and predict what is the likelihood of the patient within 5 years to identify cancer and to get cancer? And the results are surprisingly promising. And what I believe should be happening, and we're working very hard to make this dream a reality, is to be able to personalize risk assessment. When the woman does the first mammogram, to tell her what is her likelihood to be sick in 5 years, and then decide how this woman is treated. And it opens a big set of possibilities, both in developing therapeutics and also in deciding that maybe she shouldn't be screened every single year. So there are lots of opportunities, and I firmly believe that AI will change the way we're treating cancer. Thank you.